Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to describe for you how to analyze two-dimensional impacts. So let me talk about this picture right here. Oops, I gotta get my pen on. This picture right here, whoops, right here. So object A in this picture is moving, object B is at rest. So object A would have a momentum vector that I'm calling MAVA1 in this picture. All right, so now imagine after the impact, A ends up kind of moving up and right, and B ends up moving kind of down and right. So I've assigned letters and variables to these. I'm calling this momentum vector MAVA2 at an angle alpha with the positive x-axis. And this momentum vector I've called MBVB2 at an angle beta with the positive x-axis, down and to the right though instead of up and left. All right, let me describe that middle picture now. That's an important one, this one right here. So assuming A and B are not rotating, we're not talking about a rotational motion problem, then there's no reason to believe there's going to be any substantial frictional forces at this surface right here. We believe that, or therefore, the forces should be perpendicular to the surface. So the force direction on B would be kind of down and right. And I drew that here. Now I wrote it F delta T to make it an impulse. That's the difference between force and impulse, just the time factor. And I put FAB, meaning the force from A onto B. I also wrote it here in integral form, if you've had some calculus here. The total impulse on B would be the integral of f dt over that small time frame. That's not important if you've had any calculus here for the video. We could also just call it like force times delta t, where the force is some average velocity. Or I'm sorry, where FAB is the average force over the time interval. Same thing goes for object A. The force from B onto A would be kind of up and left. So if I draw the impulse, all right, that's just force times time, it would be, up and left as shown. And a really important thing to realize is that as long as we define both of these at the same time, the net impulse is zero because of Newton's third law. These forces are equal in magnitude, opposite direction. Okay, so if the net force and the net impulse is zero, that means that there's no change in momentum for the system, because impulse is what changes your momentum. And that means that all the momentum in this picture has to be equal to all of the momentum, or the total momentum in this picture. And that will allow us to write a couple of equations here. I'm going to get myself some more room here. So I can write one equation that looks like this. Conservation of momentum in this direction. I'll go ahead and call that the plus x direction. You don't really even need to put the x there, as long as you define with an arrow what direction you're talking about. And as we look at this picture, only one of those has a momentum to the right, and that momentum is what I call MAVA1. And it's to the right, so we're going to call that plus. You don't need to put the positive there if you don't want to. This animal doesn't have any momentum, so you don't have to put anything. Or if you want, you could put a zero there to at least say, yeah, I consider the second object. Okay, now let's look at the momentums in this picture. And again, remember, momentum is a vector quantity, so what that means is you apply it by direction. So if I take the MAVA2 and I break it into components, this one right here is the x component of that momentum vector, and it is adjacent to the angle alpha. So what we're going to have then is MAVA2, right, times the cosine of the angle alpha. And it's positive because it points to the right. Okay, now let's talk about the other one, and I'll go ahead and change colors. So this momentum vector The hypotenuse is mass b times VB2. We can write it in component form. That would be the x component of that momentum vector. This one is the y component of that momentum vector. And the x component is adjacent to the angle that I've called beta. That's that angle right there. Whoops. So we're going to have plus MBVB2 times the cosine of the angle that I called beta. All right, that's a B right there. Okay. Now, again, that discussion of the net force is equal to 0. That's why we can put this equal sign here, because there's no momentum change expected in any direction. All right? So there's, I'll call that equation 1 there, coming from momentum conservation in what I'm calling the x direction here. All right, next we can do the same thing in the y direction. Conservation of momentum, con of mom. And let's go ahead and do up positive. You can do down positive, doesn't matter. All right, so I'll call this equation 2. Now when we look at this picture right here, that's the before impact picture. Neither of those objects have a momentum in the y direction. So our net momentum is 0 before impact. Okay. Now we look over here. Our momentum in the y direction for mass A is this one, which is opposite alpha. So that is going to be MAVA2 sine alpha, and it's positive because that arrow is pointing in the direction that I have called positive. Okay. Now mass B's momentum vector, y component, is that one, opposite the angle beta, and it's down, so minus mass B VB2 sine of beta. Again, that's a B here, sorry about that. And again, we can put the equality here because net force is 0 during the impact. All right, so in a two-dimensional momentum problem, what you typically would do is apply momentum conservation in two directions. And here's an example of what that might look like. Now, there are two equations here, and that would allow you to solve for up to two unknowns. If you had a third unknown, then what you would do, I'll call this 3 with a maybe, is you would ask yourself, do you believe energy is conserved, specifically the kinetic energy? If the answer is yes, then you can write a third equation. If the answer is no, then you're done. You can't. You just have to hope you can solve it with the two equations you have. Now, again, if the answer is yes, if these are things like pool balls that are very, very hard, or steel bearings where there's very little material being deformed, right? So then we can say, okay, it's reasonable to say the kinetic energy, so I'm going to put if yes, based on the materials. Then we can equate the kinetic energy in this picture to the kinetic energy in this picture. Whoops. And here's what that would look like. The kinetic energy in the first picture would be 1/2 mass A times VA1 squared. And then the kinetic energy in the second picture would be 1/2 times mass A times velocity A in picture 2 squared, plus the kinetic energy for the second mass B, 1/2 mass B times velocity B in picture 2 squared. And again, the equality is if the material is very hard. So things like steel bearings or pool balls, or on the atomic scale, when you look at electron collisions or proton collisions, they don't actually ever touch because they're repelled by what's called the Coulomb force. So again, equation 3 has to be, I'll say, used with caution. Equations 1 and 2 are guaranteed. All right, as long as there's no net force acting on the system, you can be assured that that the momentum is the same in both directions, allowing for equation 1 and equation 2 to be written. Right? So I hope this video has helped you learn how to write momentum conservation equations in 2 dimensions. Have a great day.